Hello.
Yes, sir.
Sure. Okay. So, so yeah. So tell me. So have you guys gone over the dynamic programming section? If you have any questions, doubts on those first sections, right? 6.1 to 6.4, or yeah,
Sir,
yeah.
I was trying out some of the questions in the book and I couldn't understand one of the questions.
Oh, okay. Can you just say which one?
I think it was the sixth or seventh one. So there's a,
It's in the book.
it was, yeah,
Sorry.
in the book, Kleinberg Tagdor's book.
Let me open it first. Yeah, it is 6 point what? 7 you told.
So, yeah, it was based on the words and like alignment.
It is at the end of the section, chapter 6, right?
Yes. Sixth question.
6 question. Let me. It is the solved exercises or
Not solved, not solved.
unsolved exercises, right? Okay, 6 question. Okay, so in the word processor, right?
Yes.
The goal of pretty printing. So maybe I can just share it so that all of you can see also. Okay, so you will be given this text and you have to basically kind of write it up in this way, right? So and it as even as possible, right? So basically what you have to do, let's try to think about it even without reading the rest of the problem. Let's try to think what how can you convert this question into a mathematical question, right? So you have these lines, they can be short or long, right? And your goal is to kind of break it up in some way, basically join them together or something, and to get it into the even lengths as possible. Now, basically, in the initial thing, it doesn't matter each line is right. At the end of the day, you basically combine them together one by one. So all you have is the size of the words. Like first word is a call with a space, maybe so that means 4 letters. Then the me is with a space, then it will be 3 letters. And Ismail with a dot, which is some other 8 letters, and so on and so forth, right? So so basically you will be given a set of WIs, which is the length of the each of the words, okay, and your goal will be to partition, to put partitions inside. So you have this, so maybe, I mean, I'm just thinking aloud, okay, here. So you can think about it. So you have this W1, W2 till the WN, right? And your goal is to put up partitions over here in some sense, right? So basically say I1 to IT. Now what is T or T minus 1? So if I want to split it up into T different mm, uh, lines, now I don't know whether that T is given to you or not, but let's say that we have been given these t different lines kind of stuff. Your goal is to what? You want to find I1 to it minus 1 such that, so this is assuming that you want to split up into t lines, okay, such that okay, so you can think of it this way, right? So you have this set of, this is in the first line. The first line is basically the sum of the stuff. The second line is the next one, and so on and so forth, right? So if you look at let the length of the line, say Li or Lj. So what is the Lj? Sorry, let me give this breaks. Okay, so let's call this one breaks. B1 to B T, and so Li is basically the length of the ith line, right? So this is basically all the words, is the sum over all the words which are basically I is between is more than B I minus 1, or J is between and less than Bi, right? So basically this is the length of the lines that will come out. And then what we want to do, you want to kind of minimize what? So we have this breaks in the lines, right? And your goal is to minimize or make it as balanced. How do you make it as balanced? What can be a concept of making these lines as balanced? So the difference, so you have to look at the difference between the maximum length of them, right? So maximum length of Li and the minimum length of Li. And this quantity is minimized. Right. So this is one way of thinking about it. Okay. Now I don't know what is there. So maybe the problem that is given has another way of you can think of it. Instead of making this one as t different lines, one can also say that the size of the line. So size of each line is less than or equal to say some t. So that can be another parameter, and in that case you have to break it up in such a way that that is there. So the summation of each Li is less than t, and you do this whole thing. Okay, so let's see how have they defined it.
So they defined the second way.
They defined the second way. Okay, so the maximum length L. Okay, the maximum length L, and we'll assume a fixed width format. Okay, this is all for me. Formatting of W consists of partition it into lines in a word. Okay, so if this is assigned to one line, then we have this quantity is less than. Okay, so they are really okay. So this is a bit of a, a bit of a. So here, for example, we told that this line length is this quantity, right? But if you see it, so here, like after call, I counted the blank, right? But after, when the line stops here, I don't need to count the last thing, right? I don't need to count the line, the space. So this is just a particular thing. So this is nothing but one less than something. So here it will be this minus one is the length of a line, but that's fine. That is just a very minute change. And we can call an assignment word valid. Given a little partition the words into lines so that the sum of squares Okay, so they are doing it in a, okay, so they are doing it a slightly different way. Okay, good. So here, this is how we have minimized it, right? But maybe you can do it in a slightly different way. So there are multiple ways of doing it, right? The idea is same. So you want to partition it into lines, so exactly here, right? So you have this W1 to Wn, and you want to partition this whole quantities into B1 to B, say T, and so I mean maybe I should change this one, whatever is written. So this one is that length of each line is at most L, right? So let's see. I want to partition it into some lines such that what? First of all, the length of each line, right? So if Li, if I just copy it here, right? That say Li, this is the length of each line, which is basically nothing but sum of Wi, where I is between, I mean just how we wrote it here, right? So sum of Wj, j is between this and Bj minus 1 and Bj. Maybe one of them has to be not, yeah, it doesn't matter. One of them has to be strict and one of them has to be non-strict. Here they have written -1, but that's just a particular a minute thing, right? So this is length of each line, and for such that this for all I, Li minus L, sorry, Li is less than L, right? Now see, and what is the goal that I have to do? Now I have gone to the end, right? So this slack is basically, you can say that, okay, I want to minimize L minus Li. So look at, sorry, so look at the maximum slack that is there, maximum of L minus Li, and minimize this quantity. Maximum as I, minimize over the choice of B1 to BT. So this is one way of doing it. So that I want to say that, oh, I want to just minimize this whole thing at the end, right? But there is another way of doing it, right? And that is what they have done. That instead of having this such a max, min-max kind of stuff, then okay, I don't want to do all such min-max thing. Let's just minimize summation of Li minus L minus Li whole square. Now that's also is another quantity, right? It is exactly like, I mean, what is the mean that you are taking, or what is the deviation that you are taking, right? Like the standard deviation of the, so what is the other deviation? This take the absolute value and take the deviation. I forgot. You guys are, help me out with your statistics.
Variance.
No, variance is the square, right? Instead of taking the square, you can take the absolute value and take the expected value.
Isn't that absolute deviation?
Yeah, absolute deviation. Yeah, so they, I think it's a, yeah, okay, whatever. So instead of that, they are doing this variance kind of stuff. Okay, so this is the deviation that. So your goal is basically to come up with this partition such that, okay, this is just saying that each line has length less than or equal to L. I mean, that is like a important thing. And this is the minimize the slack. Now, note that as I pointed it out, I mean, it is not necessarily this is the only definition of a slack you can think of, but here they are doing it with that. You could have also used this one also. Okay, but here you are using this particular thing as a slack. So this is their definition over here. Okay, now this is the problem. Now this problem, I mean, for people who have read this section, is kind of similar to the knapsack problem, if you think of it. Okay, I mean, basic idea is same. I mean, it's a multiple knapsack you can think of. It's a kind of a multiple knapsack. So So this is the problem. Is it clear, the problem?
Yes, yes, sir, the problem is clear.
Yeah, how do you solve it? Think about it. As I told you, it's a knapsack kind of stuff. See, think of each line. So you have read the knapsack, right?
Yes, sir.
Yeah. So in knapsack, you have one knapsack and you have the weights and you try to maximize the amount of things that you can put in there. Right? But here you have multiple knapsacks, each of the same length, L, and you put them up, right? You kind of stack them up. Okay. It is not so. It is slightly easier than knapsack in the sense that you have a partition, right? So partitions are somewhere in the middle. You don't have you cannot permutate the words. The words are in a particular order, right? And but you have to ensure that this quantity is decreased. Okay. Okay, think about it. Maybe if you are still struggling of next class to come up with a solution, we can try to take a shot at it. But yeah, I also don't know the exact solution of it. I mean, must say, and whatever I did right now was just on the fly. Okay. But I think this is a very nice problem, more from the point of view of, and particularly for you guys who are like, say, you might be going into some industry or something like that and all. I mean, who would really thought of that this kind of problem, this kind of a formatting issue, say, it actually nothing but an algorithm problem, and it is actually connected to dynamic programming, right? So it kind of gives you this concept of how do you model a real life problem into a mathematical problem and then solve it. Yeah. So yeah, so don't worry. So I think this all these things, this -1, +1, and all those kind of stuff, and even this quantity, this is a sum of squares, and all those are not the main issues. I think those things, I don't believe those are the main issues. Those things can easily be, you could have replaced it with some other. I mean, even if you have a +1 over here, or even if you have instead of squares you had fourth power or something, possibly it would not have mattered too much. Okay, so don't get surprised or worried by that, but think of it. But the main issue is where do you put the boundaries, and so you of course, since it is a dynamic programming algorithm thing, so you can clearly guess that it has to be in the dynamic programming. And okay, think about it, and we may come back next class and discuss if you have not yet got the solution.
Sir,
Okay.
Yeah.
sir, I have a doubt in the section 6.3.
Okay.
There it is given that the when we are in segmented least square thing, the runtime was given a order of n cube, and then there is then it is there that order of n square can, in order of n square it can be done, but then we have to do something, it is given, but I could not understood that how it is order of n square, because here it is given that when we know, it is defined Eij, and it is given that if we know Eij minus 1, we can determine Eij in constant time. But this quantity Eij, this we are using in each step in order of n places. So actually order of n is there, and in each calculation order of 1, we sum order of 1 means ultimately.
I'm in the section 6.3. Can you say which part actually you're talking about?
I am saying in page number, sir, 266.
Okay, 266. Okay.
analyzing the algorithm, there the time complexity is
Okay, let's
given.
so first part you are fine, right? First paragraph, so which is the order n cube.
Yeah. That is fine. But in n cube to n square, I am not understanding that.
So there's a note at the end which might help.
Yeah, but there it is given that the e I to I comma j minus 1 to I e I j, that can be done in constant time. But this constant time is some n times, or n, sorry, n square times. So actually this will help, or I don't
No,
know.
if you do it constant time sum n square, then I don't. Let me just see. I mean, has anybody else has gone over it? And I mean, and if you can help him out, you can tell him while I read this thing. Has anybody have gone over this?
So,
In
could you repeat the problem? I got disconnected for a second.
no, this in 6.3 there is this, they have given this algorithm which is n cube, and in the last paragraph in this section, the authors have said that you can do it in n square. So your friend is asking, I mean, kind of, can you, if you have gone over it, can you explain what is, how it is, how they are getting n square?
So I didn't understand the exact process, but the problem was that to compute some Eij, we take order of n cube time. And in a footnote, they have said that by using some special techniques, we can compute it in order of n squared times, which would make the entire process faster.
Okay, so okay, I can see what is the confusion here, because the last line is actually a bit, this takes order n for each j for a total of order n square. We have to determine the minimum difference of to fields. Okay, so here what they are saying is that you can do the compute the minimum for each j in order n steps. So who was the person who was so this one, right? So what's the problem?
Yes, sir. This,
Yeah. So I think so. This n square thing is that you are not exactly not computing the whole. Oh. Okay, so I mean, instead of me trying to decipher it right now here, so can I ask you once? I mean, can I ask you a favor? Can you just post this problem? That I mean, can you please explain how does the n cube to n square happen in the classroom, and then we can address it. I mean, once we go over this section a bit ourselves, this part.
excuse me, sir, I could not understand
Just
what
just
is.
post a note in the classroom saying that can you just to please explain the n cube to n square. Then I mean I have to go over the write up here what they have done.
Okay, sir.
Okay. See here there was this footnote also.
Sir, I think they did not memorize the function, but they just are saying to memorize the function in this footnote.
Okay, I think what they are doing, if I understand it somewhat clearly here, that they are filling up the matrix in a different way. Okay, so they are filling up the matrix by first filling up all the ij such that I minus j equals to 1. So basically kind of the diagonal or just away from the diagonal. Okay, they're first filling up all of them in the diagonal and then goes for all of them in the off diagonal and so on and so forth. And by doing so, they're saying that it is possible to compute the each point ij. You can do this whole thing in order n steps, order constant steps. You can fill up all the n square values in order constant for each pair.
Sir,
Yeah.
so here I minus j equal to 1.
Yeah.
The number of such pairs can be n minus 1, and we have to compute the
No.
Eij.
See, so I minus j equals to 1. So see, it is about, okay, so I think this is how it's happening. Okay, so maybe this is something that I think this is what is happening. So I may be wrong here. So see, you have this matrix, right? Right. So you have this I and j. Basically, these two things, right? And for each point, you were looking at some other places and kind of computing something. Correct? Now, what I think they are saying is that you first fill up the diagonal this diagonal part, or the diagonal part is possibly is already filled up. Then you fill up the one that is just off from the diagonal. Both sides are off for the diagonal. Then you fill up the next one. Okay, and by doing so, what they are trying to say is that for whenever I have to compute each of them, so I have to compute this particular part, I will compute it at some point, whenever that my diagonal slowly moves and reaches there. To fill up any one piece, it is taking constant amount of time, not the whole thing. Okay. So for filling up one piece is taking constant number of times. And therefore, since I have n square different squares, so the total time taken will become order n square times constant. So it is says that first you compute all the ij pairs where j minus I equals to 1. Then for all the ij pairs, so for each of them, you are right that the total number of such things are total number of ij pairs as j minus I equals to 1 is n. And you are spending order n time only for that. Okay, but not order n square time.
Okay, sir. I think I understood it.
Okay, maybe there's some more things to be worked out, but yeah,
Yes, sir. I understood it.
you understand? Okay.
Thank you.
Okay, good.
Sir, I have another problem that in section 6.4, here it is given that the problem is not solved in using greedy algorithm. In page 267. And there is given an example that weights maybe w by 2 plus 1, w by 2 and w by 2. But I could not understand how being a greedy algorithm fails. One may come up with such a greedy algorithm that.
No, of course you can come up with a greedy algorithm. So don't worry about this one. I will come back to this particular part later on. Okay. Uh, it is something that will be kind of related to what we do later. You can do greedy algorithm, but then what will the running time of that greedy algorithm be? Will be the main issue.
Oh, okay.
Okay, so for example, here, how much time does it take actually? So maybe I can just explain it a bit actually for you guys. So what is the running time of this algorithm that has been told?
NW.
Okay, so the running time that has been given to here, okay, is NW. Okay, fine. Now you can also have a running time. So the greedy algorithm, you can of course create a greedy algorithm with a running time of 2 to the power n. Okay, that is certainly there. So this is using DP and this is using greedy. You can do that. There's no question about that. Okay. Now, okay, so I don't know, this is a bit detoured, but okay, fine. I will just do it this one. Now, so far you have been doing a lot of this kind of algorithms, which we are saying that, oh, this running time is linear in the input or quadratic in the input or something like that, right? What do you think? Are these two algorithms, are they polynomial in the input side, input? The running time, are these algorithms polynomial in the, are they polynomial, let's say, polynomial time complexity? Are the polynomial time complexity?
No, sir.
Okay, which is no and why?
Sir, W can be anything. I mean, that is not may not be a polynomial of n.
No, but who cares? I did say it's n. You are giving, so okay. So now good point here. So what does the polynomial means? Whenever we say an algorithm is polynomial in something, an algorithm is linear in something, right? This is the time complexity, which is a function of what? Right? We have a parameter that is gone into it, right? Anytime we do an algorithm, we have some input, right? And we have assumed that it is an n bit something. So maybe it's a graph on n vertices. But a graph on n vertices, right, is there. If I have a weighted thing, a weighted graph, I have a graph on n vertices with the weight function on the edge weights, right? So the input in this case is a graph and its weight. Similarly here, the input is a, what is the input? Input is n and w. So whenever we say polynomial, we mean polynomial in input. In fact, it is called input size. Okay. So basically, if the input has been given, then if the input is of n bit or n number of integers or some kind of stuff like that, then how much time does it take? Right. So in this respect, W can be anything in n, but W is also an input. Right? So in this setting, what do you think now? Are these two algorithms polynomial in the time complexity?
Sir, dynamic programming time complexity is polynomial. Then
Okay, but greedy?
greedy is not.
Okay, first of all, greedy is not. Everybody with agrees with him.
Yes, sir.
Okay, first thing is that greedy, the time complexity is not. Greedy is not polynomial. Okay, very good. What about dynamic programming? So he says that dynamic programming is polynomial. Everybody agrees with him?
Like assuming W is constant, it's a polynomial, but if W can vary as well, and we know
W can vary, just like n can vary, right? It's a parameter.
it shouldn't be a polynomial.
It should not be, or should be.
Should not.
Why?
Because I can choose W to be 2 to the power n.
No, it doesn't matter, but W you don't have to, you are not choosing. W is given to you. W is a part of the input.
So it's a polynomial in n times W. It's not a polynomial in n.
Yes, it's polynomial in n comma W, say. So what we mean here is a polynomial in all the input size.
Right, then it is a polynomial.
Then it's a polynomial. Do everybody agree with this thing? Okay, is this, I don't know, so maybe I can repeat it again. So see, whenever the running time of the algorithm is a function of the input size, okay, it is not a function of n, it's a function of the input. Now if the input, so think of the graphs are very easy to think, okay, in the graph has an input, plain simple graph on n vertices, the input is actually n square, or sometimes we say it's the n plus m, right? Depending on what is the, how is it given? Is it given in the adjacency matrix or the adjacency list form? Right? Fine. So the running time is a function of n plus m. So n plus m is the size of the input. Now, if it is a weighted graph, then other than the graph, you also have been given the weights on the edges, right? So that is also part of the input now. So you have three inputs now, n, m, and w. Okay. So the running time of an algorithm is considered to be a function of the input size. Okay. So in some sense, you can see the three parameters that have been given to you, n, m, and w. And the input size is something of that, n plus m plus w kind of stuff. And is the running time, and how is the learning time is a function of n, m, and w. So you can of course choose, you can say, oh, there can be a w which is as big as 2 to the power n. But then w itself is big. That means the input is big. Am I making clear this part? Or
Yes, sir.
is everybody with me? And this is a very important concept. I mean, not immediately, but within very soon, this will be very important concept. But what?
And my internet connection was unstable. I didn't listen.
Okay. So which part should I repeat here?
So last 1 minute around.
Okay, fine. So basically, whenever I give in you an algorithm, right, and I measure the input, run time, this number of steps, it is a function of the inputs. Now the inputs can have multiple parts. Okay, in a weighted graph, the inputs can have n, which is the number of vertices, m, the number of edges. It can have also the weight, right? So say if the graph is, so if the input is a weighted graph, is a graph, right? Just a plain say graph, unweighted graph, then the input has two parameters, n and m. You are right, in this case, most of the time m is just a n square at most. So things are slightly, you might say that, oh, they are kind of connected. But if the input is a weighted graph, right? Then the input is n, m, and w, the weights on the edges. So in this case, the function, the running time of any algorithm, running time of an algorithm, this is nothing but a function of the input size. Okay, the input size, right? I mean, think of it in this way. So here, so in this first case, it is a function of just n and m. In this case, this is a function of n, m, and w. Now you might say that I can choose the w to be massive, right? 2 to the power 2 to the power 2 to the power n. Yes, you can choose w, but then the input is also big, right? I mean, it is, we are not, I mean, it is a very weird thing, right? I want to say, oh, hey, come on, give me a good algorithm that makes very small number of steps. Very good. But the input is so massive that is like almost infinity, right? I should not really compare that algorithm with some other algorithm, right? I should kind of say how good an algorithm is the number of steps it makes as a function of the input size. Okay, so you should always think of these things as parameters. So if I say a function, an algorithm is linear, what do I mean? That the runtime is a linear function, okay, is a linear function of input size. Okay, if we say that an algorithm is exponential, this means that the runtime is the exponential function of input size. Note that I am not saying it is an exponential function or a linear function of n. Okay, it is always in terms of the size, okay, of the input. The algo is polynomial, then the runtime is exactly what you expect. So this is a polynomial function of input size. Okay, so it is, so you should not think of W to be, okay, can I set it to be massive compared to N? That is not the point at all. It has been given to you, it's an input. Okay, it's a parameter. Okay, so is it clear? Okay, so when we say that if some algorithm is linear or polynomial or this one, what does it mean?
Yes, sir.
Okay. Now, after, if you see it all is there, then what do you think is dynamic programming? This one, I mean, the runtime of DP for knapsack. Is it polynomial or non-polynomial? So what are the inputs? The inputs are N and W, right?
Yes,
Right.
sir.
Now, dynamic programming takes order N times W steps. Now, question is that, is dynamic programming polynomial?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir. Everybody says yes, sir.
Yes, sir.
Okay. Actually, it is not. Now, this is a very kind of a subtle place that is there. The inputs are N and W. And everywhere I'm saying it's the polynomial in the input size. Right? So what is the input size? What is the input size that is there?
Is it n plus 1?
No. Input size. Think in terms of the bits. Think in terms of binary, if you that helps you, or decimal, or anything. I don't care, but some factor. See, so your input, of course, has that you have been given this n weights, right? So W1 to Wn and this capital W, right? These are the inputs that you have been given, right? So it is not, the input is actually, so you have been so all you have to specify is the weights, correct? Of the input. The input is the weights. But what is the input size? Just think of it. I want you to solve it, okay? And all my W1 to Wn are either 1000 or between 1000 and 999. So not 999, 1000 and 10,000. Okay, so all the Wi's are between. So think of this case that the input. What is the input? Input for knapsack. This is the W1 to Wn and capital W, right? And I have been also told you that W1, all the Wi's are between 10,000 or 1,000 and 9999, right? And W is basically the 10,000. Okay, and N is some number. I mean, N is some N is a, and you have some N, right? Let's say let me fix this N to be equals to say N is N is 20. What is the input size?
So each number is 16 bits and we have n plus 1 numbers.
Right. Or if you want to think of it in the world of decimal is also fine. See, to specify Wi, you only need 4 digits. Right? To specify Wi, the weight of the size of Wi is not 1000, it is just 4. Right? Size of W is just 5, not 10,000. So while this has been given as an input, but the input size, the size of the input is not that, but there is a way of compressing things and giving it to you. Right? The information has been given to you all of that is your input, but it is not that if I have to specify 10,000 number, I have to give you 10,000 balls, so you can count and see, oh, okay, now good, we have 10,000 balls. I can write that 10,000 in just 5 decimals or some number of the bits. So the input size in this setting is nothing but log of Wi, log of base 2 or 10 or whatever you want to think of, doesn't matter, summation over I plus log of W. So in some sense, you can say that since you can always assume that Wi is less than W and all, this is like n times log of W. Okay, the W is the input, but the size of the W is not W. Size of the W is log of W. Okay, so in dynamic programming, if you have an algorithm that takes n W steps, it is actually not polynomial in n and W in input size. Why? Because this NW is not polynomial in n and log W. It is exponential in that because W is exponential in that log W. Hello.
Yes, sir.
Yes, sir.
Is it clear? This is a very subtle point, okay, but it's a very important point. Okay. It's a very, very important point. So this knapsack, although it manages to do something in a very neat way, actually the running time is an exponential in the input size. Okay. So in some sense, what we have is that both these two algorithms are actually not polynomial. Okay. In fact, we will see it in maybe in 3 weeks from now or 2 weeks from now that you cannot have a polynomial time algorithm for knapsack. You cannot. Okay, I mean, there's some asterisks there, there's some conditions, but we'll come to that. If you have heard of, how many of you have heard of P versus NP, or P is not equal to NP question? Have anybody of you heard of it?
We've heard of the question, that's it. We don't understand it.
Yeah, you don't understand it, that's fine. But how many of you have heard of it? I just want to know. Or how many of you have not heard of it at all? So there are,
I
you have not,
didn't.
you have not heard of it.
I didn't heard.
Okay, so it has a long story and it is one of the most celebrated questions in mathematics right now. It is one of the 6 remaining clay math million dollar questions and all. I will come tell the story of this whole thing and also this problem, and we will do that. Yeah, this is connected to this. Okay, so coming back here. So both of these algorithms are not polynomial. Okay, but you can still see that these are slightly different things over here, right? Both of them are not polynomial, but somehow this top one feels like polynomial, right? And that is what they wanted to differentiate over here to some level. That it is exponential in the weight of W, in the input size of W, but not exponential in N. Okay, so it is, and here actually if you just go over this perfectly, this whole thing, this will not be actually N times W, it will be this actually. And this will be kind of exponential in both the parameters. So this one is exponential in one parameter, this is exponential in both parameters. Okay, so there is a subtle difference between these two quantities. So this is of course better than this, because this dynamic programming is not exponential in N, but is exponential in log W. And greedy algorithm is exponential in both. Okay. So in some sense you can think that, okay, if somebody comes up and guarantees me that W is less than, W is a polynomial in N, maximum value of W is polynomial in N, yeah, then you have a good case. Okay, so this is what has been kind of told. So yeah, I think I took a bit detour over here, but this is something I think was a very important concept that we will have to deal with pretty soon in this course. Okay, so I mean, this helps you to see how to compare these two algorithms. So don't think the dynamic programming means, wow, you have done a great job. It is not done a great job, but it is better than greedy. Both of them are exponential. One is exponential in both the parameters, the other one is exponential in one parameter. Okay. Okay, fine. Is this clear?
Yes, sir.
Yes.
Okay, good. Some more questions? Any more questions about dynamic programming and this part and all? Do you have any? Okay. Have you guys tried to solve the shortest path problem between, I mean, singles for shortest path problem with negative weights, negative edges?
Yes.
Yes, sir.
Could you guys solve it?
Yes.
Okay. How many of you tried but failed? I mean, there are only 15 of you. Can you just say it? I mean, I've tried but could not get much headway or something.
That was an assignment question, right?
That was an assignment question? No.
It
Oh,
is
that was an assignment question? Okay.
Yes, sir. Like the current assignment.
Okay, okay. So have you guys all done this?
yes, sir.
All of you? Is there anybody who has not yet done it? Or could not
So
do?
I haven't reached that problem yet. It's the last one.
Okay, fine, okay. So I think I mean there are not many of you are today. So what I will do is that I will stop today, and instead yeah. So we will meet on Tuesday again, of course. And you guys, as far as I understand, at least most of you have read the first 4 chapters of dynamic programming. Please go ahead and read the other parts of dynamic programming. Okay, chapter 6.5 to 6.8, and try these problems at the back. And again, if you have any doubt, okay, while reading this, while reading something, as soon as you have a doubt, like say like somebody told that I didn't understand how that n cube goes down to n square. Okay, it would be slightly helpful for us if you guys kind of tell us beforehand, so that before class I can just have a quick look at it and be sure about what to uh, uh, what all to discuss and all. So maybe it's a good idea if you just can post it on Classroom. Okay, I mean you can ask a question to all in Classroom, right? That I mean, can you please? I mean, I'm struggling to understand this part or something, or I'm struggling to understand this question, or something like that, or I don't follow how this statement is coming through. Okay, of course, if you are if anybody have, I mean, you feel free to discuss with you guys. Means if somebody posts a Classroom comment or asking a question, somebody else answers it. I mean, you are feel free to answer your friend's question. Okay, and else, of course, we will kind of go over it and come back and address it in the class. Okay, the other thing is, yeah, on Tuesday, I will discuss the single source shortest path problem. If for whoever has not been able to solve it, and some other dynamic programming problems are there. Okay. Okay, fine. So let's if you have no other questions, so let's stop today, and we will meet again on Tuesday.
Sir,
Yeah.
I had, sir, can you check my solution to the question that you had given the other day? I had emailed you that.
Oh, you have emailed me that one, right? So I will take a look at it. Okay. Okay, thanks.
Thank you, sir.
Thank you, sir.